Okay, so I want to talk about expanding the chemistry functionality in Mathematica, and I kind of want to just give some motivation for this initially. So I'll tell you where I'm coming from. I got a PhD in theoretical physical chemistry, and when I started graduate school, I had no programming experience whatsoever. They just take you in based on your math test scores. And immediately, I was a TA in a physical chemistry lab and was introduced to Mathematica, and I did all my simulations, all my work in Mathematica. And so I've really felt like more people ought to be able to do chemistry in Mathematica. Just the ability to, I mean, everybody here knows the ability to experiment in the notebook interface, to get a hands-on feel for things, can really help students to learn. And so I think that expanding what Mathematica does in chemistry is a worthwhile goal. So first we take a look at what has been available in the Wolfram language. So we've always had import-export. You can import PDB structures. You can, and this gives you a nice 3D ribbon diagram. Let's see, I thought it was 3D. And then, let's see. Yeah, there we go. And you can also import MOL files or XYZ files, and you can essentially look at a static image or a 3D image. You can get a few properties. You can get the vertex types, the edge rules, these things that have graph names. But essentially, they're not computable documents. They are, let's see, we don't need you. They're not computable objects. They're static. You can't change them. So next we have chemical data, which was introduced in version 6. And chemical data allows you to query for properties of the thousands of chemicals in the knowledge base. We have this data has been curated from sources such as NIST or PubChem or ChemSpider. And it's got lots of experimental properties. So I can ask for the combustion heat of propane. I can ask for Henry's law constant, isobaric heat capacity at a particular temperature using thermodynamic data. And so chemical data has been around for a while, and it was vastly expanded in version 10. So next, we have entity value, which came online much later, adding a little bit more capability. So we can ask for properties of a group of molecules, and we can make a data set of it, and it's very nice. But it's still static. It still depends upon curators having found the data and brought it to you. Next, we have the Wolfram data repository. I put a few entity stores in the Wolfram data repository. The GDB9 database. This is a database of over 133,000 chemicals. And so you can download that by prepending this resource data object to your entity stores. You can query for a random entity. It has various properties, including experimental but also calculated properties. You can look at the data in a data set. And so again, it's static. You can't change the entities. And so there are a few more of these. I highly recommend checking those out. And then finally, there's Wolfram Alpha, where you can ask natural language input, like how many carbon atoms in 5.46 kilograms of propane. I recently hooked that one up myself. You could ask how many, what's the pH of 2 molar acetic acid? You can ask questions that lead to a step-by-step answer. You could ask for the, let's see, you could do your stoichiometry homework. 0.2 molar methane plus oxygen goes to 7 milliliters water plus CO2. It'll balance the reaction for you, and you can get, you can do step-by-step. Let's see. That's dynamic, so we will go to the cached version. And so we can walk you through step-by-step how to solve these types of problems. And so that's the capabilities for chemistry in the Wolfram language so far. But there has always been a demand for more. So here I'm looking at a bunch of questions that were asked on the Stack Exchange. So people talk about the fact that there's no stereochemistry information in chemical data, how the fact that you can't, the functions used to visualize things aren't exposed to the user, so their options aren't known, there's no documentation. So people ask, how could I add a legend to one of these plots? How could I access the internal function that plots the molecule specifically? They want to change the color. They want to plot random DNA strings. Let's see. They want to fake a molecule plot when we don't have the information. Some people have gone through and even made molecular orbital visualizations in Wolfram language. Yeah, I asked like at least 3 of these questions, to be honest. That was before I had access to the source code. And very recently, this happened actually only just a few months ago while I was still working on what I'm going to show you today. A user who's actually, I think he's listed as a consultant for the company, he came up with the molecule viewer package. And so this addresses the fact that in the standard chemical data, you don't have any double bonds and you can't do highlighting. And so, but it's, again, it's fairly static. You have to import MOL files or retrieve information from chemical data or PubChem. And so I'm interested in introducing a Wolfram language molecule data structure. So who would be interested in having a computable data object? Okay, yeah, me and Bob, definitely. I suspect, I don't know about Bob, but I suspect that we both kind of joined the company with the express purpose of getting to this position so that we could introduce this, this package. The fact that we also needed jobs at the time probably was serendipity. Okay, so I think the target audience at first might be chemistry students and educators. Constructing a molecule and manipulating it, changing out a carbon for a hydrogen, changing an oxygen, a carbonyl, protonating an acetic acid, and could be gives a real hands-on feel. And so I feel like that could be very helpful to students. And then researchers and grad students are mainly, when I was a grad student, I wanted it, so that's what I'm thinking of. Computational chemists, they in cheminformatics or molecular modeling. These are the people we think might be interested in having a computable chemical object. What form would it take? It would be similar to a graph, because like a graph, it has the atoms are vertices, the bonds are edges. We can use the graph capabilities in Mathematica to do computations, although it's kind of roundabout. So we can make a graph here out of benzophenone. It looks fairly, from a chemical standpoint, it doesn't look very good, but we could grab information from chemical data and make the layout of the graph look better. You could even ask chemical data specifically for a structure graph, and this gives you a graph. So this is a computable object. You can change its highlighting, but more specifically, you can use functions like find shortest path to find the longest shortest path in this molecule. It would be from this hydrogen to this, and it loops on around. And so in some ways, people are already using the graph capabilities to do chemical computations. But there's a lot of differences that are not covered by the graph. So the vertices are not distinct in a graph. Duplicate vertices are pruned. Let's see, vertex and edge properties like charge, isotope, bond order. We can add those to a graph, but they're not taken into account in graph computations. Whereas in chemistry, they're very, very important. And then hyperedges. This is a relationship between more than two vertices. So it's not an edge, it's a hyperedge. So here I'm specifically talking about stereo elements, where you have 3, 4, or 5 atoms with a specific 3D spatial relationship. So that's what it might look like. What might you call it? The thought is to call it a molecule. You could say, hey, that doesn't work because the IUPAC defines a molecule as something that is connected. There can't be any disconnected pieces, and it can't have a charge, which is a little bit too restricted for us. If you go to the IUPAC, you can find they have a molecular entity, which is any constitutionally or isotopically distinct atom, molecule, ion pair, radical, blah, blah, blah. So that pretty much covers it, but it would be far too confusing to call something a molecular entity in the Wolfram language. Another very precise definition or name would be an atom container, which is what's used by the CDK toolkit, because that's literally what it is. It just houses a bunch of atoms, but it just doesn't have the right ring. So for now, we'll use molecule. What would the input form for a molecule be? So you have to at least give it the atoms and the bonds. You could give it, there are other things you can give it. You can give it properties, you can give it stereo elements, but at the very least you have to give it atoms and bonds. So we could do that. We could create a molecule right here with 3 carbon atoms and 2 bonds. And then we could query, having just created this, we could query the knowledge base to find any chemical data entities that match that. And we find that we have propane in there at least 6 times with different isotopic substitutions. We can set the properties for any atoms here using the property head. This is what we do in graph. So here we're saying the formal charge of the middle carbon atom is 1, so we put a carbocation. And we create this. We can look at it. Yes, sure enough, there's a positive charge right there. Notice that the hydrogens were added by default, by valence. It's okay. And so if we wanted to look at the input form of the molecule after we created it, we see that the properties have moved to the end in an association. It's a very convenient method for storing the molecule. You can create a molecule from an entity, take one of those deuterated propanes, and create a molecule, and then we can look at the input form of it. And we see that the mass number property for all of the hydrogens has been set to 2. And it's got vertex coordinates because those were available in the chemical data packlet.
What's that command?
Pretty form. Yes. So it's in general utilities. So it's in a packlet.
It's not the official function.
It is. Yeah. It's there. It's on everybody's Wolfram language distribution, but it's not expressly documented. But I really feel like everybody should use it because it's fantastic. It really lays out.
I break it at any moment.
I like to be risky and use undocumented functions. Okay, so you could create a molecule from an entity. You could create a molecule from any name, right? So we can store a list of names in a persistent object, load it in, and then just find any random chemical name from that list and create a molecule from it. Here we go. We just created 2H-imidazole. We can look at the input form of it. We can look at the molecule plot of it. Okay. And then we can search the knowledge base to see if we have such an entity. Chemical entity. 17. So we don't, apparently. We might have the hydrogen at a different position. But the last time I used random, I got one and found one. Okay. You can also use a smile string, which is a very compact form of writing out the chemical graph. So again, I have a persistent object here. I grab a random smile string and create an object from it. And And when we plot it, and so to read this, we start it at oxygen. Let's see, let's make that guy a little bit bigger. To read a smile string, you read it from left to right. Let's find out which. So this was the very first oxygen. It's connected to a carbon, as we see in the string. That carbon is double bonded to an oxygen, but it's also then bonded to this ring structure. It's bonded to this aromatic carbon, which is part of a ring, and the rings are denoted by these by the integer digits. I highly recommend going and looking at smile strings. It's going to be the easiest way to enter in a molecule. I mean, what I love about that, so say we take that smile string, and now we make a new molecule, but we edit it. So let's say on some random carbon here, I'm just going to put put a big, long hydrocarbon chain on it. It's that easy. That's why people, for storing large amounts of molecules where you don't have any know anything about them other than their structure, the smile string is the preferred serialization format. Okay, now we move on. So now you might ask about visualization. Let's again take a look at what we've done so far. If we look at ATP, you can look at the molecule plot or the color structure diagram. Note that the color structure diagram shows no stereochemistry information, and the 3D plot has no double bonds, which is something I've heard complaints about from users. So we introduced in entity value the multi-bond molecule plot earlier in the year, or last year. But we still don't have stereochemistry information there because it's not in the packlet. But that could be solved with with the new package. So if we create two molecules here using their chemical names, we can make adenosine triphosphate. We can look at molecule 1. There we go. You see the stereochemistry is indicated. We can ask whether M1 is a substructure of M2. And we find that it is. But if we ask the other way around, we would right. Right. Okay. Right. Okay. All right. I swear I just hit Apple C. So we could ask if M2 was a substructure of M1. No, it's not. And then we could actually find the substructure, find the adenosine in the adenosine triphosphate, and highlight it. So that's neat. We could create a molecule out of fullerene. We could plot it, and we could ask to highlight only the 5-membered rings. That's what this is. This is a smart string. It's like a smile string, but it allows patterns. So what this says is it's a 5-membered ring, carbon atoms, and this ampersand stands for, or no, that's whatever the at symbol is, stands for any kind of ring bond. But here we're saying there are 5 bonded within a ring. So this only highlights the 5-membered rings. And then also we can look, so this I think will be useful for teaching. So you can make a molecule out of L-alanine, and you see that it does have stereochemistry information. So we plot it labeling the indices. You can look at the inside and see that it's got a clockwise rotation. What this means is that atom number 2, this carbon, is chiral, and the ligands around it are 1, 3, 4, and 9, and that if you look down the bond from atom 1 to atom 2, you'll find atoms 3, 4, and 9 to be in a clockwise direction. It's a little bit confusing, but we could change that and just make it counterclockwise. And let's see, did I enter this in? Right, so then you can do a molecule plot of them and stare down the axis of that bond. If you look from here, you find blue or green, blue, purple, in a counterclockwise direction, whereas here it's green, blue, purple in a clockwise direction. And so that can give a hands-on feeling for what we mean by stereochemistry when we teach it. Let's see, we could skip this because we're running out of time. Well, let's see, just show, you can query for QSAR properties, quantitative structure-activity relationship, which is essentially querying for a large number of numeric property values, and then these are used in machine learning applications to predict molecular properties or biological activity. Another method for predicting properties based on structure from the 1980s was the Joback method, which is hooked up in Alpha right now, where you could decompose a molecule into all these different substructures and add up the contributions for each of these to try and come up with an estimate for the melting point, enthalpy, heat of fusion, and whatnot. It's not the best estimation method, but it's very easy to implement. Okay, we could do fingerprint similarity searching. We've got hooked up a wide variety of different types of fingerprints, and what we could do, so here we read in, I'm not going to do this right now, it takes about 17 seconds to read in these 10,000 molecules. We create a molecule nearest function from that, and then we can query that for the molecules that are most similar to a random choice, a random molecule. So here's our random molecule, and then we query the nearest function for the 5 molecules in this set that were most similar. And then you can visualize the results. Wait, Oh. Okay. So I should probably have read that in a little differently. Okay, so we can do fingerprint similarity searching. We can do 3D structure manipulation. So we take a molecule from this long smile string, and we can manipulate it. Here, we'll make things a little bit larger. We can query for bond lengths, bond angles. Let's look at this carbon-hydrogen bond length. It's 1.09 angstroms. We could try and make that larger or smaller, and you can watch the force field energy increase wildly. You could minimize it back to its original state. You could, theoretically, do a constrained minimization. So select this atom and this atom, and say I'd like them to, right now they're 12 angstroms apart, I'd like you to find a geometry where they're only 6 angstroms apart. Let's see, and we constrain it. And this is where we got. And so you found the molecule, there are enough rotatable bonds where it was able to find a conformation where those were only 6 angstroms apart. Notice the energy was 223 kilocalories per mole. If we remove that constraint and then minimize again, we can find a much lower energy.